This this is the last session of the theory portion of this chapter. Quite a change from the previous two, which were the longest and second longest in the book. This chapter is effectively only about six and a bit pages, so polished off fairly quickly, right? Now, so as I was saying in the previous chapter, I'll mention a bit that about other factors, greater complexities in the physics, the analysis, the math, the modelling of the hydrogen atom. So we can get then sort of corrections to the energy eigenvalues that we've predicted in the theory we've done so far. And these corrections, like finer measurements of the energy, and you get how am I going to put it here? Don't I thought I had it done. All right. Well, there are other effects, phenomena going on which influence the energy eigenvalues, and hence the wave functions and the lobes and probability densities and so forth. And here are like three effects, three other phenomena that would change your energy eigenfunctions and your energy eigenvalues and your energy eigenfunctions, right? One is just effects that occur because you're bringing special relativity into your quantum mechanics, but that involves, that's first year masters, that's Dirac's equation, which weds, we've talked about this before, which weds special relativity and quantum mechanics. Bottom line is that when you have a relativistic treatment of quantum mechanics, and you apply that treatment, like you apply the Dirac equation to the hydrogen atom, you do get differences from what we've done so far due to the relativistic effects. So special relativity will have an influence, will change the energy eigenvalues somewhat, right? Another one is, now we'll talk a little bit about this next chapter, but both the electron and the nucleus, both of them, they have magnetic moments, like you can imagine, in a sense, it's just a rather crude analogy, but imagine within a proton, or this charge, imagine charge almost like a fluid. So this fluid is rotating around inside the proton or the electron. So you have an internal magnetic moment. It's always acting like a little magnet due to flow of charge. Right? That's a classical mechanical analogy, and that's all it is, just an analogy, right? But the point is, electron and the nucleus both have a magnetic moment. So in a sense, this little magnet, if you like, the electron, is creating a magnetic field which acts on the charge of the nucleus. Right? Now it's a small effect, but it's there, and vice versa, because the protons in the nucleus, the neutrons as well. I think they also. I think neutrons also have a magnetic moment. Is that true? I'm not sure. Probably cancelled out because it's neutral. Anyway, so the protons in the nucleus generate a magnetic field which influences the electron. So it goes both ways. It can get quite complicated. I mean, you could say, like the magnetic moment of the electron and the magnetic moment of the nucleus, those two interact with the electron's orbital angular momentum, right? And it's this interaction with the orbital angular momentum that is the part of the topic of next chapter, which is definitely not 6 pages, it's quite a bit longer. Let me count: 2, 4, 6, 8, 10, 12 pages, so it's double the length of this chapter, right? And speaking of next chapter, so what are the topics? So we'll do more on the addition of angular momenta. It gets a bit more complicated. And we'll be adding orbital and spin angular momenta, so for an electron or for a particle. So yeah, 2 kinds of angular momentum. We mentioned previous, previous chapter, 2 chapters ago. Well, this would be coming. Previous sessions. That you can add the angular momentum of a single particle's spin plus its orbital angular momentum, and spin orbit coupling. So the spin has an influence on the orbit, and then a little bit of talk on relativistic effects, relativity, bringing that in for the first time, and the so-called Zeeman effect. So you get splitting of allowed energy levels. The energy eigenvalues split, they change slightly when you switch on a magnetic field, if the atom's in a magnetic field. And there are various forms of that. So yeah, so quite a lot of theory in the next chapter. Alright? Okay, so next chapter will be about this second effect that changes things, the relatively simplified model that we've been using so far. And the third one, subtle, right, and small, but coming from quantum field theory, I'm just wondering whether I mention what's going on there. I don't think I will. You need to know a lot more quantum mechanics. Alright, but yeah, just bottom line for this is that just accept that there are phenomena that come out of quantum field theory. That's the quantum mechanics of fields, electromagnetic field, and later we'll do the chromodynamic field for quarks, and the quantized field that create a force on the quarks, bind the quarks, they're called gluons for obvious reasons. All right. Now, so that's sort of a footnote. So getting a little bit back to our model, the simplified model, the energy eigenvalues here, they do not depend on L or M. Well, you have to go back a session or so to see the formula for the eigenvalues, and there's no mention of L or M's in it, right? So that means those energy levels, the energy eigenfunctions, are degenerate in terms of L and M. So if you put in the L and M, you'll get this fold, that means many times, degeneracy. Remember that for each value of L, you have 2L plus 1 possible values of M. M, remember, being the eigenvalue of the component of your angular momentum, L, along the z-axis. So this sum here is over all possible L values you can have for a given N. Okay, so the possible number of states will depend on the number of L's, and for each L you have 2 to the L plus 1 possible M's. So the total number will be this. For each L, that's where the sum is, you'll have this many terms. And you get an extra 2 here. You may wonder what this 2 comes from. And it's just due to the fact that there are 2 spins. Okay? There are 2 spin states. So that's what this 2 is. Now for homework, if you like doing math, number theory type problems, prove that that is just 2n squared. Okay, L I think ranges from 0 to n minus 1. Okay, I mean you need some relation between L